Yeah.
Yeah, I'm ready.
Hello and good afternoon, everyone. So thank you all for being here. We have a great attendance, and that's great because we have also a very interesting topic. So today we are very happy to have with us Professor Roma Schenkely from the Tomas Bata University, Czech Republic. He's an expert in a topic which is currently quite hot, that of large language models, and we are particularly going to see in this talk how this new technology that we know it's been very disruptive, that just in a matter of a couple of years has gone from something very marginal to be prominent in all aspects of life, can also be very important, very useful in combination with evolutionary algorithms and help us to design better evolutionary algorithms. So we have this talk that I'm sure you will enjoy. Of course, at the end of the talk, we will have plenty of time for all your questions and doubts, and we are very glad to have someone who is very knowledgeable in this area who can really answer those questions. So please, a warm welcome to the speaker.
Recording is
Yeah, recording is on.
Okay, so welcome again. For me, it's pleasure to be here in Málaga because I love the city. I've been here already maybe 10 times, also with my family. It's super easy to get to Czech Republic, especially we have like I said like 5 flights per day to different cities like Brno, Prague, Pardubice, Ostrava. So a lot of Ryanair flights are going to between the Málaga and Czech Republic. It's very popular here. The Czechs like Málaga, you know, because you have also own beer. But today is not about the the Czech and culture and so on. We will go into the super hot topic, which is like there are 2 abbreviations. One is ADLs, automatic design loop, and another one is AAD, which is automatic algorithm discovery. This is 2 things that are now moving the research field and especially a lot of applied field. So, and we will just talk about the LLM-driven algorithm discovery and tuning. Since we are here in the evolution and combination, let's say, classes, and this is more related to the, let's say, evolution learning and iterative principles. So it connects both, you know, like the evolution principles are connected to the LLM, and we are using this evolution principle LLM to evolve another evolution algorithms, for example. So you will see that there are many things that we can do and how we can basically join these fields together. So I will try to be as much illustrative as possible, including, let's say, a lot of high-level descriptions. I will not go into some tabular data and all these analysis and things. So I will try to explain you a lot of interesting things that happened past 2/3 years in this field, because we know in 2022 September or November, I think that November 22nd, 2022. Since GPT has been, let's say, released to the public, there was a huge revolution. Okay, so we will have a nice talk. And firstly, I would like to. Okay, first I would like to introduce my lab. Of course, this is GPT generated. I'm here, and this is like the core members. We are the 6 researchers in our lab, plus a lot of PhD students. And maybe I heard that someone was already visiting us, so maybe recognize the person. So I'm from AI Lab, and we are doing nice research in meta-heuristic algorithms, benchmarking, analysis of position heuristics, and of course we are connecting these things together with automatic machine learning, because the things that how you optimize the ML models and so on can be automated, and especially LLM-EC, because this is our now interesting field. Okay, so this is the overview of today's talk. I was instructed to not to, let's say, bore you too much, like maybe 1 hour, 1 hour and 15 minutes. I have 162 slides for you. You know, that 40 of them are backup. If you are very interested, I can show you a lot of some nice stuff. But let's say 120 is like the main one. So just briefly, we will just talk about the black box optimization and how we select and configure the algorithms. What is the current state of the art? Let's say, then we will change the talk. I will talk about the possible role of generative AI. You know, the LLMs and generative AI in such tasks. Very simple use cases. You know, that from literature. Then I will talk about the Gen AI frameworks and AI assistants, because in our AI, we have developed one of these Gen AI frameworks that has been used for interesting stuff. And I will show you the path, you know, what you can do, and from the most simple steps towards the full framework, what you can do, how you can evolve automatically this, as I said, this automatic algorithm discovery or auto design loop. And of course, there are a lot of challenges and the future outlook. And of course, then if we have a time, I will go a little bit deeper into two most prominent tools, which is the EASE. This is from our laboratory. The EASE stands for Effortless Algorithm Solution Evolution. Very easy to solve it with EASE. You know, like you have a problem, you call the EASE, it will solve it, and it's easily solved. And then another one, this is from my friends in Netherlands, in Leiden. It's called LAMEA, which is a large language evolutionary or large evolutionary models and the evolutionary algorithm and so on. So it's a strange abbreviation. So let's just look at this. So the introduction, I think that you understand what's there. No, so this is basically we talk about the black box optimization. If you would like to, let's say, talk about the field of the evolution computation. So we know that it's like a derivative-free optimization. Basically, we don't know nothing what is happening inside because sometimes the constraints, the function is unknown, and so on, non-existent, unexploitable. And what we do is just we possibly put some input, we get some output, we measure that, we store it, and say, okay, so we have some data. Just the question: do you think that this in real life we do solve? That we have something that we have absolutely zero idea about what's happening? More or less, no. You know, the black box optimization is something that doesn't really exist in, let's say, practical applicable domain, because we always have something. We always have some simulation, we have some model, we have some benchmark function. So we basically instruct the algorithm to work as a black box, but in real life, we usually don't have such problems too much. But there are examples. So there's can be some legacy code, so we have no idea what is inside. There can be some simulation models, real-life experiments, crash tests, and so on. Because this is the real things about the black box optimization. But the thing is that sometimes, you know, that it gives us some challenges, because if we do have some crash tests or chemical reactions, of course, we are not treating it in this way. So we are not putting some random input and get some output, because we don't want to blow the factory, or we don't want to crash 100,000 cars and so on. So basically, in real life, if we are doing some crash tests because we don't want to crash 1,000 real cars or something. So we always have some model, and we always calculate something. We have some high-level simulations, we have some expectation, and so on. So this is usually the role or the place where we really need some sophisticated and smart algorithms and clever algorithms that can solve such a problems, where in real life we have something, we run only some simulations, we have some few samples of data, or we have some high-level information about the objective function. It's not fully black box, but we at least know something, but we want to treat it as a black box. So basically, this is you have no idea, you know, what's there. So basically, what we solve mostly is how much it will cost us. So we solve two questions. You know, this is the first one. You know, with the cost, we usually mean the measure of the resources which we need to evaluate the function. Usually in real life, if we want to run all these simulation of crash tests and so on, so it costs money, you know, to run simulators and so on. It costs money. So we usually somehow always convert money. So we have a cheap functions, like some benchmarking or some tests or some proof of concept, we can run it for 1,000, 1,000 millions of evaluations. It's still fine. It's if someone is paying the electricity bill, it's fine. You know, and then we of course have some very costly functions where we need to think about, really, we need to very, very clearly and cleverly, you know, find a way how to navigate towards some cost function. So this is usually what is how we basically somehow classify the problem. So the algorithms, the evolution algorithms, meta-heuristics are mostly designed for black box optimization problems, because there's the idea that there should be no knowledge about the problems, which is basically true, because the algorithm has no knowledge about the algorithm, except that we calculate it as a cost function. The cost function will calculate it as a simulation. So in real life, we mostly deal with the cheap functions, because we love to have a lot of evaluations, but means that we work on the base evaluations. So we call it meta-heuristics, which is some computation procedure, where we just try to find some optimal solution. We try to improve the candidate, and we measure the quality, and so on. But there's the second question: which algorithm is the best for our problem settings? You know, what's the best algorithm? Should we select it? Shall we design own algorithm? You know, this is, let's say, the $1 million question. If you solve really deep, it's a very costly problem. And answer for that, this is a credit to my colleagues in Leiden. They always use this picture, because they simply say that the biology is equal to engineering, because the nature selection is a universal algorithmic process, and then it's very important mindless mechanism that can generate complexity, intelligence, and even consciousness without the need for design or central planning. So there's just this evolution process, this iterative training can really evolve really, really complex systems. So let's look at that. Because we know what we want to do. We have the black box optimization. We work with the meta-heuristic, which is designed for that. We need to somehow always think about what to solve and how to solve it. But now let's just think about how to select the algorithm or configure it. So what's the issue here? So we know that the field of meta-heuristics, we develop or use the optimization algorithms for global optimization or combinatorial optimization. Global optimization means that it's in the real domain. Combinatorial, we just, you know, like a traveling salesman problem, so on, zeros and ones and integers. These algorithms are typical bioinformatics, which follows the previous picture. So these algorithms should be fine. You know, they are natural, they are complex, they somehow evolve the solution. But again, the question is, they are mostly based on the evolution process used for intelligence. The question is how to select the right algorithm. You know, I have a problem, I want to solve it. I have some benchmark functions, I want to solve these benchmark functions. I have some competition, I want to win the competition. But with which algorithm? Especially how to configure such an algorithm. So you know that every algorithm has some hyperparameters. You need to set up the parameters of the algorithm before the optimization or before the model is evolved, and then you can run the model. And especially without the no free lunch universe. Thanks to the no free lunch, we are studying computer science, because if there will be some universal holy grail algorithm that will solve everything, you know what to do. And what is very surprisingly, the automatic algorithm selection was established in 1976, just right after the foundation of Evolutionary computation in 1964. So I say, okay, we think that, okay, 1976, it has to be solved. No, it's still not solved till today. In 1976, they were thinking about the mapping of instance features to the algorithm performance. So it means that they simply think about, okay, so we have some problem, solve the problem. Let's look at let's say this is the instance of the problem. Let's look at the features of the problem, describe the features, and then look at the performance and try to find some links. Okay, if I'm solving the problem that looks like this, has this type of the cost function surfaces and so on, And this is the performance of the algorithm. Let's make a linkage. Of course, okay, so there's a mistake. In 1976, it was brutal work, you know, handcrafted models. Okay, if it's this, then it is this. If it's this, then it is. Nowadays, this is machine learning models. You can use the XGBoost, some random forest. If you can somehow get the features of the problem you are solving and the performance, which also requires a lot of runtime to get all these features, you can train some machine learning model to predict what will be your, let's say, I don't know, performance at the end of the day. But again, there's a new problem. You don't have features for that. You need to rerun everything and just train again, see it, and so on. So it's not helping very much, you know. It's a very complicated problem. And especially with this. I don't know if you already heard about this. I suppose that I think that you were already instructed, but every time in every class in my home university, I always surprise the students with a new algorithm. The most cited algorithm 2 years ago was a squirrel jumping algorithm. I saw also on some papers like crazy chicken frog or something like that. Or there was a gravitation black hole gradient algorithm, or there's, let's say, there's thousands of algorithms already, you know, and there's already a bestiary of these algorithms. You can just simply look at that, you know, because it was just driven by this idea about the madness, which is basically absolutely continuous. And I love the logo, you know, from this bestiary. Just gotta catch them all and get these things all. But now think about that. We have a space of maybe 1,000 algorithms. How to select the good one? Okay, and especially how to do it. Because if you want to design the algorithm, this is a typical workflow, you know. So we get some inspiration. In case of this crazy algorithm, we get some metaphor, like, you know, you just look outside and there's a leaf falling out of the tree. Maybe I can write a leaf falling algorithm because it's moving somehow, you know, or the birds are flying somewhere. So basically, you get some inspiration or metaphor. Then you write the algorithm, you benchmark it, and if you are lucky, you can get some publication if you send it to some, you know, whatever journal. But there's also some issues. The metaphors, for the sake of metaphors, because then you want to get rid of the metaphors, you create a new one, and so on. And there was a nice paper from my friend from Camacho, from Christian Camacho. He was working in Belgium in Iridia Labs. Now he's working in Ljubljana. And he has written a very criticizing paper that all these algorithms can be decomposed to some just very simple algorithm like PSO and so on. And there's also selective benchmarking. Maybe you can say, okay, let's get rid of all of these, and use genetic programming. I don't know did you already have genetic programming here in classes? No? Well, it's just another level of, let's say, evolutionary process. So instead of optimizing some numbers, you are working with a set of terminals, non-terminals, grammar, and you are evolving the problem. It's like you play with the Lego. You take the different bricks and build some machine, home, and so on. So instead of, how linear regression looks like. You have an equation, and you want to find A and B. So you can run the algorithm to find A and B. The genetic programming or symbolic regression means that you are evolving full formula, including these parameters. So instead of getting the model and find the best optimization parameters for this model, you evolve the whole model. Genetic programming sounds fine. Maybe you can create the program of the algorithm. But come on, just think about that. Some differential evolution, PSO or GA, will need to search for all these terminals, non-terminals, functions, if operators in huge search space. That's like, 99.999% is infeasible solution which doesn't work. The genetic programmings are fine for some particular use cases in math. They are not good in creating the working code for your algorithm. So what's next? Fortunately, in 2015, started the ideas, let's create a modular algorithms. We have a modular CMAES evolution strategy. We have modular differential evolution. We have a modular PSO. It's called PSOX. So basically, you have a different modules of the algorithms. Okay, this module is doing this. This module is this mutation. This module is this type of the crossover. This is different crossover. Let's use this adaptivity of here. So you have different modules, and again, you can handcraft or automatically somehow craft the algorithms. But again, in differential evolution, there was like a huge 1,000, let's say 10,000, 10,000 combinations of the modules. Because differential evolution, I suppose you know. No, you don't know differential evolution. Okay, so this is the evolution algorithm where you have a couple of different mutations, crossovers, and so on. And just think about this huge combination space if you just decompose it to different modules. And then you want to, let's say, compose another algorithm. It's 10,000s of combinations or 100,000 combinations. It's difficult work for CMAES or PSO and so on. PSO, particle swarm optimizer, great. So again, you can have these cognitive function, this can adaptivity, inertia weight, this. You can turn it off. Again, a lot of combinations. Of course, you can also run the auto configuration, because you need to set up the hyperparameters. You can set up the space. Okay, so the population size can be 20, 25, 30, 35, 40, 45, 50. Let's select all this. Okay, parameter C1, C2 can be 1.5, 1.6, 1.8, and so on. Again, there's a huge amount of combinations, including this, and so on. You can also switch the algorithms during the run. Call them warm start. What does it mean? Either you start the algorithm from completely random position without any knowledge, or you can start it with some good promising place, with some parameters that work from the last experiment and so on. How to combine all these things together? There's a huge space for searching. Manual metaphors, come on, it doesn't work. You can set up some crazy jumping frog algorithm. Why not? But in real research, this is so huge. And how to do it somehow easily. So, okay, now we understand. We have some modules. We understand about the hyperparameters. So we can set up all these configurations. We can find some modules. We can put things together. It works. We have a tool to automate writing the code, right? After 2022 and GPT, we have a tool to write the code, right? We have an idea about the modules, about the hyperparameters, about everything. What about to put these things together? So, can we use the LLMs or GenAI to put all the knowledge about the modules, hyperparameters, setups, cold start, warm start, switching, all these things together? The knowledge that is basically in thousands and thousands of research papers. Can we put it together and use the LLMs? Why not? Because, we know the LLMs can be used for chatting, not good here, but we can chat about the algorithm. We can explain the stuff, why it works, why it has been selected. We can write an email. Okay, this is not good in the meta-heuristics. Maybe meta-heuristics can optimize the emails or writing emails, but summarize the text, translate something, but the most important thing, the coding. So if we have some idea, we can explain something, we can summarize something, we can code something. So we can just now use it. So basically, we just add the second part and now join it together. And we will have now the big space for, we can call it automatic algorithm discovery or auto design loop, where we, of course, we will use all the knowledge from the meta-heuristics, from the black box optimization, from the nature process, selection, crossover, iteration, and put all the things together and let's say create very interesting concepts. So, well, and we are getting here, let's say, to core parameters. Since 2022 and 23, there was many interesting papers that are addressing the similar tasks. The LLMs, if we just think about the optimization, just now think about the evolution and computation and the LLMs together. We will then slowly move to these, let's say, automatic design. The LLMs and optimizing of the prompts. This is good. You know, the evolutionary algorithms can cooperate with the LLMs, so can optimize the prompts, optimize the data selection, inputs, or maybe the responses, and so on. The LLMs can recommend the hyperparameters. For example, what is the best population size for my problem? Because this is the knowledge which I was talking about the hyperparameters, about the modules. You can work separately, you can use it this way, or you can use it either way. So it can be always, there can be LLMs with EC or LLMs for EC, or EC with LLMs or EC for LLMs. You know, there are so many things you can combine together. But the LLMs can also act as optimizer. You can try it. Ask the GPT that, for example, you have this type of the function. What is the best solution? Well, it can hallucinate, or it can find something in the inherent memory. Or there can be LLM-driven research assistants, which are already using the evolution principle. So we are basically getting from this small step towards these full algorithmic models designed by LLMs. And I will show you some first tries. This was in 2023, and I said, okay, how to connect the evolution computation LLMs. Now we are talking about the LLMs with evolution computation, not for. No, so basically, there was GPT 3.5, the genetic algorithm, and it was used to optimize the prompts. And they find out that the response of the GPT was much more accurate and better and faster. So it works. Another thing, but this is like throwing a lot of money out of the window, is in 2024, the LLMs has been used for tuning of the evolution strategy, so these hyperparameters. But this is about the knowledge, which I said that is in the problem, the knowledge about the modules, knowledge about the hyperparameters. Basically, you simply describe, okay, I have this type of the optimization problem, and I want to solve it with LLM, with evolution, with evolution strategies. Okay, dear GPT, what is the best setting for that? The GPT will describe you something, and basically then you see already this feedback. So it means that if you're not satisfied too much, you prompt it again. Sort of learning, sort of evolution. So we are getting there. The LLMs sometimes can play a role of the evolution algorithm. So basically, you just simply you describe your proposal of the problem, and then you ask the LLM to sample or evaluate the molecular optimization. You just simply describe the problem and ask it to solve it. And then you just make some updates and so on, and just run in a circle. So it's again somewhere at the end of 2024, 2025. The LLMs can work as the evolutionary computation, but of course, this is like very, very, very high level approach. And now we are getting even to more complex things. I don't know if you heard about this. This is the research assistants. Sakana.ai. No? This is a very interesting project, which means that it will replace all the PhD students, all the researchers in the world. Of course, nonsense, it doesn't work. The idea was, again, the evolution and computation and iterative process. So you write some idea into the LLM. It will evolve some, let's say, research plans. It creates the experiments, write the code, run the experiments. Of course, it will update. You see this evolution loop. So it will update everything, depends on the results. Then you get some results, write a paper or research, or master thesis or PhD thesis, and publish it. Automatically, they call it automatic PhD student. Well, to deploy it, it takes, wow, incredible amount of time to try to run it. Of course, it's not fully open source, you need to pay for something and so on. But the idea was, can we improve iteratively some ideas? What does remind it to you? This is the evolution, this is nature selection. So they have done it. And of course, the same, of course, if someone releases something, Google always come into the market. Google created so-called AI co-scientists. And again, you see these small loops. This is the same. You just simply write what you want to do. It will create a research proposal. It will make some tournament and evolution improvement of the ideas, of the plan, everything, run it, and then get the results. So this is these research co-scientists. And in 2023, somewhere around this, we had together with the friends in Leiden, we had the idea. Let's do this. The general idea behind the LLM and ETSI, not just to use it to optimize the prompts or asking the GPT 3.5 for, hey, what is the best parameter setup for PSO or OSMA or Evolutionary, or even, let's say, even more strange idea. Hey, this is a special function. Can you solve it? Of course it can, because the LLM knows about the 10,000 papers that is describing where exactly the global optima is. But if you want to do it in, let's say, black box, it will not work. So this is the general idea we had together. So you specify the problem. The LLM will create the code. We create the algorithms. Then it will benchmark it, evaluate, test it if there is nothing wrong. And then again, it can select and reprompt it back. And this can happen in the loops until you will get the best algorithm automatically. So this is the idea we had. This is evolutionary loop for getting the evolutionary algorithm. So this is how we can use the LLMs to automate the process. Of course, now we just get into 2024. I don't know if you heard about this. This is called Fun Search. Again, from Google. They are just picking the best ideas. The Fun Search, I will just put one. The Fun Search works like this. You just simply specify what do you want to do. There's a pre-trained LLM. It's called function search. It was designed for mathematical formulas, for the programs, and so on. It will create a candidate programs, candidate mathematical formulas, evaluate it, find the best one, keep it in some population, and then prompt that. So improve the prompt, like, okay, I have found this one was best, this one was best. Can you do it again? Until you get the new program, new formula. So this was the Fun Search. It was released in Nature paper. Currently, it has like 10,000 of citations. It's from DeepMind. This is just some iteration. So Fun Search is an AI framework for DeepMind discovering new mathematical conjectures and algorithms using LLMs with evolutionary approach. So basically, all this learning, improvement, and interactive things is involved here. Only the LLM generates the candidate solution to programs, and it will become the best. So you see that these things works. And okay. And of course, there was already new interesting frameworks. This is from Liu Fei group from Hong Kong. They already came up with the EOH framework, where you basically evolve the heuristics. So it's the same as a Fun Search, only you're evolving the heuristics. So you just specify the problem, you create a new heuristics, you evaluate it, then you have a population of heuristics, you search there, you find some offstreams, how to cross over it, make some feedback, and so on. And basically, this was focused mainly for combinatorial optimization, because they have designed all these steps for most of the combinatorial optimization, like bin packing problem, traveling salesman problem, so it can evolve the solver. for these problems. This EOH is from 2024, later 2025 improvement. Then we have re-evolve, is basically evolution. It's very similar to EOH, only it includes so-called reflection. The reflection means that there's some reasoning about the previous solution, and it can calculate, let's say, the short-term and long-term reflections. So it can evolve, let's say, new heuristics based on the benchmarking results, based on the historical, let's say, reasonings and analysis and so on. And then, or not then, before, we came, this is from AI from Zlín, this is 101. This is open source modular framework. I will talk more about more details later. For automating the creation and refinement of solutions, so we are using the evolutionary loop again learning for crafting the algorithmic solution, but not only the algorithms. We are the only framework that can evolve. Evolution algorithms, AI pipeline, classifiers, images, codes, poems, jokes, whatever, all together. So we are not, let's say, only tied to the evolution of computation. And I will tell you more details. And our friends in Leiden, this is this general idea, they create this LLM. Here it is, large language model evolutionary algorithm. Why it's a large language model evolutionary algorithm? Why just connect these two things together? Because it makes sense. You specify the problem, you specify the role, initialize the search, and then, again, the LLM, create the algorithms, you load the algorithm, check if it's okay, the code is fine, everything is fine in the algorithm, because you know what is the main problem if you try to generate the code with the LLM? For example, you prompted, hey, create a PSO algorithm to solve this problem. It usually forgets all the dimensions. You said this is 10-dimensional problem, and then you check the code, and there's 4 dimensions from 1 to 9. Where's the 10? You know, or there are some mistakes. You know, it just jumps across the iterations. So basically, you check for the errors. You evaluate. They have own. It's called IOH profile. You know, iterative optimization heuristic profile. This super complex software where you can basically benchmark the algorithms. You get the performance. You store it in history, and then you just simply decide: shall we improve it or not? If yes, you go again and again and again. So basically, this is how the thing works, because the LLMs has some idea about the modular algorithms or the modules of the algorithms. There's some idea about the hyperparameter setups for the current problems. Of course, you can force it there. You need to describe it here in the prompts, and so on. And the last of these, we have ETSI, we have LLM. And of course, in 2025, in May, the Google came again with their own, it's called Alpha Evolve. It's just an improvement of fun search, which means that it's not only fun searching of mathematical functions, but of course, it's the same as LLM or ETSI, but it came later. So we have been faster. And of course, it's an open source, you need to pay for Gemini and so on. And it's for general purpose algorithm covering search, geometry, and logic problems. It's not open source, it's not reproducible, because you have no idea what it's doing inside. But the main thing is LLMs ensemble. It's also using the different LLMs that are cooperating, fighting, competing together. There's like agents, and they are co-working together to get some interesting things. So basically, they just improve it with the more agents. And okay. This is the current state. We have an ETSI, we have a LLM, we have got Google Alpha Evolve. You can iteratively improve and evolve any kind of the algorithm you want. In case of Alpha Evolve, we have no idea what is happening there. In case of LLM, you can somehow control the process. But how we get there, last 3 years. And now I want to show you how we get to this point and what was the challenges during these steps and during this path. Okay, so I will show you 4 case studies from 2023, 2024, 2025 in this very fastly evolving field how we use the GPT or other LLMs to help to create a new meta heuristics, and how we, somewhere in the middle of the path, we simply decided, we should do it fully automatic. So then we started developing the ease. So the first case study, it was presented in Gecko Conference 2023, and I have to say this was the first peer-reviewed paper about usage of LLMs to evolve any kind of the algorithm. So it was leveraging large language models for generation of novel meta-heuristic optimization algorithm. We have submitted to some swarm sessions, so it was full of swarm and crazy algorithms, but we didn't care because the idea was about that. So we have used the GPT-4 model that now is legacy model with this very, very small, tiny context. It was super difficult to get something working. Training data was up to September, and we have used manually. We have to do it manually with GPT, chat. It was, come on. But the question was, does the LLM GPT-4 provide an accurate description of meta-heuristics? Can it identify unique components? This is modular design, the components. Can it propose a hybrid methods for specific scenarios? Put these components together. And does the reasoning make sense? Of course. And can GPT serve as assistant during the development of heuristics? So this was the idea. Nothing, no automatization, no full benchmarks, no full search, and so on. Just these questions. If we create a question, we get some super place scheme, but we just set up 4 tasks to propose the feasible candidates for hybridization. So we asked the GPT, okay, what is the best candidates to take modules from? Can you reason about it? Can you identify and describe these components and so on? We asked the GPT to propose 2 novel algorithms and provide a pseudocode and implementation and to run it. So this was the first test. If the GPT-4 can do this without any flaws and mistakes and so on, because this was the base of the overall idea. Can we then automate it, and how? And what is the challenges? What are the mistakes there? What are the lessons learned? So basically, to get the code and make it run. So first one was the task selection. So we asked the GPT, hey, can you provide a list of 6 swarm-based algorithms? As I said again, we have submitted to swarm session, with 5 swarm, that have shown promising performance, global optimization, and about the unique characteristics and so on. Quite, straightforward prompt, and see if the generative AI can do something about it. It just replied, okay, use the PSO or Google search. Artificially calling that one is quite good. Greyhawk is like and then the SOMA. By the way, the SOMA is from my university from 1995 and 1999. So it's not this. It's not in bestiary. So this is good. And the whale optimization algorithm. Maybe what do you think? Why whale optimization algorithm? This algorithm is the most cited algorithm in machine learning. They have used the whale algorithm in most of the optimization of weights of networks. I don't know why, but it's the most cited algorithm from machine learning. Okay, so and we've been happy. That was fine. It worked quite well. Okay, so this was the task A. It worked. And then we asked for the reasoning for that. Why? Because this is important, because we need to decompose all the steps of this automatic process and see the mistakes, how the generative AI can make the mistakes. So we provide the selection, and then it was simplified Google search, it's meta-heuristic algorithm, which is simplified by blah, 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 and so on. And the most important is the land-flight search strategy, which is employed in here, introduce randomness that can help escape the local optima. It's fine. This is quite correct. We like it. It's okay. So basically, the generative AI can explain the choices of the modules or the algorithms. Now we simply say, okay, you select the algorithm. Can you identify the most prominent components from this algorithm that can help us? It was very strange. The GPT always provides us 2 components. We never prompted how much, let's say, how many of these components. Always gave us 2. So in PSO, it was written, use the inertia weight because of blah, 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 blah. It affects the convergence speeds. Quite good. And which is correct. And then the problem started. You know, the PSO used the personal global best, and now it's like positions or some balance between personal updates, you know, blah, 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 avoid something. It was not good. It promoted cooperation between the particles. Personal global best doesn't promote any cooperation. No? So basically now, this is the hallucinations. So we see, okay, one was fine, the second one was clear hallucination. So we need to take care about this. But at the end, for these 6 algorithms, we got these, let's say, always 2 components, which can be very promising and important. Next task was, because this is the problem of the automated crafting of the algorithms. Hey, can you put these things somehow together, make some hybrid algorithm? So, and the 2 scenarios, algorithm promotes population diversity, and as I already said, we want to solve a real life problem because we are the engineers. We are now in a factory, we want to solve the problem, and the problem is expensive. So I don't want the algorithm that runs for 10,000, 100,000 iterations. So let's do this. We got 2 algorithms. Some enhanced swamp exploration, exploitation, optimization, ESEO. You know what is the best on the generative AI? If you ask it to some new algorithm, it also gives you some crazy name. So you don't need to think about the name. And there was a nice algorithm. It was written, divide the population to subpopulations. For subpopulation A, use PSO. For subpopulation B, use some combination of Levi flights and artificial big colon. Sounds good. And makes sense. Then, for the expense scenario, it's called limited evaluations for optimizer. It combines the components from 4 algorithms. Sorry, 3. Again, I will not read it, but the last point was important. For each employed B, perform a local search. This is not for expensive optimization problem where you have only very limited, let's say, cost function evaluations. You cannot perform local search for every particle that is somewhere. So this one algorithm was wrong. So the GPT or generative AI was hallucinating. So, okay, you have to look at that. And then implementation was quite easy. We asked, provide the pseudocode, we got the pseudocode. This is the best, you know, writing of the papers. I remember 5 years ago, if someone asked me, write a pseudocode, it took me maybe 1 week. Now it's like 5 seconds, you know, just to get the working pseudocode. And of course, you need to check it. Okay, we asked for the Python code, we got the Python code, it was great. And the final task was very important. We asked the GPT-4 to provide detailed reasoning for the choices when designing these hybrid algorithms. And this is when the funny thing started. So they provided for this limited, it has very, let's say, critical flaws. There was inaccuracies, hallucinations, all these. We asked for this, why did you employ this local search? It's increasing the, but then it started to saying, oh no, it's fine. Thank you for that. Maybe change it. Use another local search. Come on. So I said this local search is wrong, and it started. Okay, let's use another local search. So there was really thing, and we're also starting to write some adaptive learning mechanism. We look at the code. There was nothing adaptive. So we saw that that's not good, but somehow it worked. The first one algorithm was good. Divide the subpopulations, run something, exchange the information. This is something that always works. You know, if you have some, it's like let's say two teams that are solving the task. One team is solving the task, another solving tasks, and then you exchange some information. It can improve the teams to be even better. And then they start solving and so on and exchange some information, team members and so on. This always works. So this was fine. So if you look at the observations, This was the first study. The good thing is that the generative AI absolutely understands what you want to do. You know, so it can select the algorithm, it can describe the hybrid design, maybe some initial reasoning is quite okay. Working Python code, pseudocode, everything is fine. The bad thing is that this component selection, if you start asking for details, it's usually start some hallucinating and do something and so on. Maybe if we switch to maybe deep research mode, it will be better. But we were working with just basic AI. The ugly thing was the hallucinations. The thing is that in this paper, we haven't studied the performance. We didn't run the code. We just simply want to say that if it makes sense, if we really rely on that. So let's look at the case study B, which is the performance. So the same model, same data, same platform, again, everything manually. And this was the experiment setup. So I will just read it now. Define the benchmark set. So we asked the GPT, okay, where to test the algorithm. Propose a novel differential evolution. Sorry, you don't know the, but just think about propose any kind of the evolution algorithm. Let's say mutation strategy with better performance, provide a pseudocode, and do the benchmarking. Okay, so let's see if this thing will do. So if you ask with the GPT, can you provide a list of 30 benchmark functions for optimizers and so on? Perfect. Including the code. You don't need to find anything, you need to check, of course, the code with the equations, randomly, if it's okay, if it makes sense. So this was fine, it was super. So we get the 30 functions, and the thing what we was thinking that that all these functions will be checked. They were already in some really good benchmark sets. Nothing was changed. The name was changed. The function was changed. So it really came up with a solid, let's say, rigorous benchmark set. Now we ask, hey, you've got differential evolution. You've got some mutation strategy. So, for you, don't care about what does it mean. So we just ask for some different mutation strategy in the differential evolution. And the GPT say, okay, let's have some DE instead of run dynamic switch one bin something. So different mutation strategy. In this mutation strategy, run one bin means that the idea is I will select 3 other candidates from the population, make a difference, there's one difference between 2, and add it to the third one. The idea of differential evolution is that, okay, I have difference between 2 solutions, and now I will look, if I take this difference to another solution, maybe they will be the same. Something similar, something good. Okay, a lot of text. So this is, the GPT will simply describe the process. So with some probability, we replace some individual with best so far, then with some probability PB, replace the individual with another one, and create some equation, and so on. Quite good reasoning. It also added 2 hyperparameters, but it also suggests some value. And we asked, hey, can you provide the pseudocode? Again, super easy. We get the pseudocode. It was running. We ask for a code. Easy stuff. We get the code. And now was the benchmarking. So we simply prompted, okay, so you have the baseline. You improve the baseline, so test it against the baseline. This is basically the setup of the benchmark. So in 10, 30 dimensions, the population size is 50 or 100, or basically 10D or 30D, more or less. There was some minimum number of iterations. There was some hyperparameter setup. There was some these functions and so on. And now we looked for the results. And then this in small dimensional, we can say that basically this our proposed, let's say the new proposed algorithm, there was a 30 wins, 6 ties, 11 lose. In high dimensional space, it's 17,112. So basically, in high dimensional space, the algorithm was working even better than the original baseline. So the things, what was the lesson learned from this? The lesson learned was, okay, we just simply take something from 1995, which was the strategy. We take something from 1995, prompt it to GPT-4, ask to improve it, and we got immediately something that improved the performance because it was working better on higher functions. So basically, it was working. And in other words, and this was the end of 2023, and we just think about, also with the guys from the Leiden, we said, if the GPT, this was the first case study, can reason selection of the things and hybridize and it worked more or less. If we ask to improve one particular module, it also worked and improves the selection. Can we do it automatically? Can we do it in some, again, evolutionary way? Okay, there was a case study C. It was presented in GECO in Melbourne, 2024, and was called Critical Examination of LLMs in Iterative Refining. Now we have this iterative process. So the specification was GPT-4 again model. At the time we call it GPT-4 Turbo because we are using API. The context window was already heavily increased. Training data was up to December 2023. Platform, we already used own app. Finally, not this manual, chatting with the GPT, copying the code somewhere, running the benchmarks and so on. And we have used some model parameters because you know that the GPT model, have you tried to play with this API already from GPT? It has a temperature, all these parameters we can set up. So we already trying to work with the parameters and different temperatures. This is the basic of our ETSI. So we already developed the own app to run some codes to see to see what is happening, to set up the parameters, to see the functions, also to count tokens because we want to know how much it cost us, to run this. And he was the scheme. So okay, we take the baseline, and we have already, because we are working automatically with API, with the own app, we have created a system of 3 prompts. It's called system, initial, and repetitive. So basically, the system prompt is telling you what to do. The initial simply set up the roles and so on and so on. And then you evaluate the algorithms if you are satisfied or not. System prompt. This is super important. So you write that you are expert in designing new innovative multi-heuristic optimizers. You are also a master Python coder. This is very important. And now you reply with Python code only. This is extremely important because otherwise the GPT or AI will simply put all this stuff like, hey, this is a great idea. Here is your code. You cannot run this. You just want only the code. No, just blah, 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 blah around. And also some hotfixes. Make sure all those functions are properly counted, return Python code, which is complete, run without further modifications, keep the class, template, and so on. This was the system prompt. That is put it every time, in every iteration, just to remind the GPT what to do and how to do it. The initial prompt was, again, what is the task? Your task is to design the meta heuristics and install 12 continuous test functions. One is unimodal for blah, blah, blah. So you basically somehow describe the problem. You get some high-level description of the problem and use my current algorithm as a template. So you specify what is the baseline, what is your template, some code, because you want to run it automatically in some benchmarking. So you want all these classes, functions, outputs, so to say. And basically specify the baseline with the Python code. And now you think about what was the repetitive prompt. This was the same. Your task is to modify the latest one. The goal is the better performance. So we didn't instruct the LLM how exactly, because maybe it will not understand. You know, if you say, hey, the performance is 25.2% better than the previous time. No, even you don't understand, nor the LLM. So, and now see what's happening. So this is the scoring. The negative scores means that we are worse than the starting baseline because we start with the code template. We want to improve it. And the score is calculated from over the benchmarks because there was 12 functions. So basically, if you improve in 6 and you worst in 6, you are 0, and so on. The first iteration was better. You know, we got better. The next one was even better. And then the things get worse. And now maybe why? What is happening? Well, let's look at this and this. This is, for example, how the LLMs is creating these improvements. This is the baseline. And this is what is happening. So basically, it added some more hyperparameters, explanations. So it's some self-parameters, you know, some adaptation and so on. This is also great on GPT, that you can put 2 codes and ask for explanation of differences. But let's have a closer look. What is the here? So we start at baseline and we add some different strategy. We add also the archive. Because if you have an archive of all solutions, this can help you to get, if something gets stuck, it can help you to get out of the, let's say, local optima. So basically it's say, okay, there's a good idea. Also the population size was increased from 20 to 100. It improved, you know, searching. Then it made the archive longer, adjust the parameters, and make some adaptation of the control parameters. This, of course, worked, you know, because if you have a larger archive, larger variety, diversity of the solutions, you have adaptive parameters, it worked. But then what happened? That it just changed the mutation strategy. Now, this is a spoiler. This is 1995 strategy. The previous one was 2014. So it rolled back to the original baseline. And then it was rolling back again and again. It was trying to increase the population size. So the LLM was trying to increase the population size, but was keeping the 1995 baseline. So basically, the LLM didn't understand, you know, what is happening. So we didn't improve. We also checked the temperature. You see, almost no influence. The temperature doesn't have too much influence, you know, how much randomness is there. But what was quite nice, and this is very important, and that's why we were starting to thinking, not about the meta heuristics, but about any AI models, any algorithm. This is the CC 2022 competition. So this is the competition about the evolutionary algorithms. I don't know if you know about this IEEE CC or Gecko, BBOB benchmarks. So but every year there's a competition and the algorithms are, let's say, competing about each other in big benchmark. This is the winner. This is the second place. This is the score. And this is our algorithms. And this is the third one. So basically, what we have done, we have used 1995 algorithm to prompt the GPT with the system, iterative, and initial prompt, and simply say, improve it. The experiment has been done in a couple of minutes, and we beat it, the third algorithm, and we get very, very close to the second one. So just think about that. You are a researcher, you want to beat the algorithm. Maybe these guys were working on these algorithms for half a year. It takes us a couple of minutes to be better than the third one and be very close to the second one. Just prompting the LLM, the Gen AI, very cleverly prompt, because the prompt, there was all the lesson learned from these A and B session, these case studies, to be better. So what was the observations? The positive output, we created a number of the algorithms with better performance at the baseline, of course. And then was a challenge. The most effective modification basically tend to occur on the earlier, and then it's the iterative process is screwed. So we need to think about what change. There was a breakthrough, 7 versions was even better than the top 3 algorithm from 2022. Next step, how to improve it? What about the feedback? And now we are getting to 2025. And this is my paper, was presented in April. It was called Open and Closed Source Models for LLM-generated Methods Solving Engineering Precision Problem. We get a problem from Continental company. And they said, oh, we are solving these problems for 3 years already. And I said, okay, give it to me. We solve it, in 1 day. And we solve it with this iterative process. And because we know that there's a problem with this iteration, it can get worse, it can do these hallucinations. So we simply think about that. So we already use the ETSI framework because we already had it. We have used the iterative design of the LLM with feedback, but with instructed feedback. Again, the same 3 prompts. We use some stopping criteria, 20 working codes. So basically, if we get 20 working algorithms, let's stop it for maximum 40 iterations of the framework. In comparison, we have used another algorithms to compare. We started with random search. So we simply say to the algorithm, hey, this is a random search, which can theoretically solve this engineering problem. Of course, it can. Maybe it can be lucky. It can solve the problem. We said, okay, let's start with this and evolve something interesting. But to avoid the problems, decreasing the quality and something, we simply make a repetitive prompt, try to improve the last algorithms, return only the code. But then we simply instructed, what are the results? What are the statistics? So basically, we take more context to the LLM because the LLM remembers the changes of the code, so we can map what change made what, and maybe revert back to some better results. And basically, this is the let's say part of the repetitive prompt. So basically, we simply write what is the mean of the function, what is the statistics for Wilcoxon test, and so on and so on with some p-values. So basically, we get a lot of context. And well, as a result, I will just click it. So we have used GPT-4o, GPT-4o mini. We have used also open source, Llama 3.1, a big one, 70 billion parameters. We have used Cloud Sonnet 3.5. We start with random search. This is the winner of 2019 competition, this algorithm. And if you look at the result, the cloud was able to get even better results than the winning algorithm from 2019 competition for engineering problems. CMAES, like, and so on, and then and so on and so on. So again, we have solved, it was some control engineering problem, time delay problem with near local optimum, near boundary optimum, and so on. So the global optimum, which is very, very close to the boundaries in 10-dimensional search space, was very difficult to get there. But the cloud was able to give us the code, the working algorithm to evolve iteratively, that we're able to solve the problem even better than the state-of-the-art algorithms. So this was the idea. Of course, there are some problems. What you saw here was this step. So level 0, LLM can use the assistant. So it can help you with the code, with some reasoning. It can propose the recombinations of the algorithms components. That was the case study on impartization. It can propose the new algorithms, computer verifications at random, or it can run everything on the feedback. And well, what are the problems? Depends on the quality and structure of the prompts. Because if you don't write the right prompts, you will not get the very good results, of course. And yeah, I'll just click it. Oops. The confidence loss is very high, of course, because you involve third party costs. You need to pay to GPT, you need to pay to Gemini, to run it, and so on. again, shall we follow the evolution mutation part or to be more open? So, not just iteratively refining the algorithms, recombine the algorithms together, some modules. So shall we do something else? We have no idea. The benchmarking is in early stages. How to benchmark something that is evolved by AI? Nobody knows what is the best, let's say, strategies for that. So there are no guidelines, and especially ethical concerns. I will just stick there for a couple of minutes, a couple of seconds. This is very important. Authorship, plagiarism, novelty, citations, and so on. Just think about that. You are asking the LLM to give you a new algorithm, but the algorithm is always not new because it somehow is getting the knowledge from the LLM, which has been training on corpora of thousands and thousands of research papers about the algorithms. Who is the author of the idea? From which, let's say, code it takes this part? From which paper it takes this? From research? From which research? We don't know, because it's basically impossible because the LLM is providing you the code. How you can identify that this part of the code is from this paper, this function is from this paper, this calculation from this? It's impossible. So basically, there is no change of scientific continuity. You cannot simply say, okay, because you know that, for example, typical science, someone is creating something, another one is improving his work, cite his work. Another guy is using this work for some application inside this one and this one. So basically, there's a nice chain. Nowadays, you can generate anything, and basically nobody knows from which source then. That's the problem. For future, not for now, for future. And of course, there's ethical concerns in case of replicability, explainability. Replicability. That's why we are using this iterative process, because every time we get something new, which can be better or worse. And the explainability, how to explain why the LLM just put this exactly there, where and there. So it's quite a problem. So before we will just get to some wrap up about these two frameworks which I mentioned. I think I still have like 10 minutes to get this 75 once I started. So this is important message for all of you. The AI basically is not a magic spell, because we should always balance the innovation with the caution. In the AI era, PhD postdocs, researchers can gain very powerful collaborator. It can really help you, with all this designing of the algorithms and crafting of pipelines and so on. But of course, at the same time, these AI assistants I show you, they can handle boring literature reviews, propose some experiments, tweaks, exploit the computation, letting users focus on creative insights. Means that you can do the creative stuff, not just this boring stuff. So basically, it has boosted production dramatically. That's true. But it's not the magic. We always need to have this skepticism, because this is what I show you in this first case study. This is the same GPT-4 or even 4.0 that can be used in the frameworks, or I don't know, or the same Gemini the Google is now using in the Alpha Evolve and so on, which sometimes was not accurate in some reasoning and so on. So basically, there must be some skepticism always. And we should always use the LLMs to assist us, not to replace, of course, us. It can be engineers and so on. And to find the balance, let's say, partnership, So we should always spot the errors, guide the search and so on, maybe to improve the prompts and so on, and really reason what is happening and so on. So this is, let's say, how we get to the path, to create these automatic frameworks, just from this very simple prompting reasoning to this performance, to the feedback, to the interactive feedback, and we get to the ease. And now we'll just simply show you a few slides for each of the prominent frameworks. It stands for Effortless Algorithmic Solution Evolution. The framework is written in Python. It's using .NET front end. It has a front end. We are the only ones. Haha. You know, the Google AlphaML doesn't have a front end. We have it. So there's a modularity, it's fully modular, so you can change it. If you want to evolve this, if you want to evolve that, you want to keep this evaluator, you want to keep that, you want to use this test, this kind of test, you can use it. You can run any LLM you want, or SLM. So there's a built-in connectors for the LLMs and our APIs, and of course it's open source. We just support your customization. And it's well documented. Each component, generation, testing, analysis, evaluation can be customized or replaced, which is adaptable to diverse program domains and workflows. And thanks to flexible design, it can use to optimize or evolve machine learning models, AI pipelines, data analysis modules, or other bio-inspired heuristic algorithms. Because if you simply say, what do you want to do, how to evaluate it, it will do for you. Of course, you need to check the results, integrity, quality, tests, and so on. And just want to show you that it's not easy job. It takes us 2 years to evolve it. This is the full benchmark, and this is the full architecture. This is the main important core, the LLM, And then basically, you write what you want to do. As I said, these 3 prompts, like system, initial, and so on. So basically, what is the role? What do you want to solve? How you want to solve? Where is the data? How to evaluate the things? So basically, it will create these functions. It will, via the connector, connect the LLM. It will give you the solution. You can also run some tests for the code, unit test, and so on, what you want. If there is some error, you can feed it back to the LLM to instruct, hey, there was an error in the code, and okay, improve it. You can run the analysis. For example, what kind of, I don't know, if you evolve some AI pipeline, we can analyze any other components, like what is the code complexity, time complexity, runtime, whatever. You can, these are, let's say, these are not mandatory intentional. Evaluation means that, of course, you need to evaluate the quality because you need to instruct the feedback to the algorithm for evaluation. Because you need to get it back to the LLM. How to improve it? If you are not satisfied, you just get back all that. So this is how you can evolve what you want. At the end of this presentation, and I will stop it there, is a QR code for the video, how we use it to evolve nice pictures or poems or jokes and something, or not the code because it will take a lot of time. And nobody wanted to look at the video, which has like 2 hours, so it has 10 minutes. So another one, so this was ETSI. Another one is Lamea, from the friends from Netherlands. I already showed you this scheme. So basically, it's more or less the same, only they are using their own profile. And they are using a little bit different prompts. They put everything into the one prompt, and they are using feedback prompt. And they said the most important keyword, your task is to design novel meta heuristics. If you remove this word, it will not work. It will start creating some random stuff, hallucinate, and so on. If you simply say, I want to do something novel, something original, something nice, it will really do. So you see again how it should handle some mind-render task, which is evaluated. Your task is to write the optimization in Python, and so on. So the Lamea is only using a different structure of the prompt, not the system, initial, and iterative. It's using the full prompt as let's say, initial one, and the feedback prompt. So basically, you see that again how it works. There's also video here how they use it not only for the evolution algorithm development, but also for example, basic classifier, something like a KNN, and so because you simply say, okay, here's the data, I want to classifier, evolve it, and that's it. It worked. And does it work? So this is the result from Lamea. So here in Málaga, there was a conference, GECO, Genetic Evolution Conference. I was the winner of the competition. Automatically designed algorithm was the winner of the competition, also a year before. And this is just some graph that there was a maximization problem. that this GPT-4 things has been the higher score. What was funny, it was also shown by the guy from Leiden that the LLM generates algorithm also, the LLM also generates the name. You know, there was many hundreds iterations of this llama and the ease, and this is, you know, how it works. You know, there was enhanced adaptive evolution, search, something, quantum stuff, and so on. You can see that there was like combining covariance metrics, adaptive or dynamics firewall or quantum flux ultra defined algorithm. This is like, you know, super, yeah, like from, this is like from the Back to the Future movie, you know, the quantum flux adaptive something enhanced super algorithm. But it worked. This one was the winner of the competition. You know, it's very crazy name, but it worked. You know? And very similarly to the ease and what I showed you with the code, that even Llama can show you where's the mutation of this code. So you have the iteration number 1, then you have another iteration, and the LLM can explain and color what's the difference. So for example, you start with the algorithm. This is a HPO, the hyperparameter optimization, because it changed the parameters to something different. You know, also it updated comments to explain what was happening, you know, in the model. It added new mutation, new some strategy. So it takes the code, another code, put it together in the next iteration and can explain, which is very good because you know what is happening and why. And of course, in Leiden, they are a little bit more ahead of us if it is, because EASE is more, let's say, universal framework. We are also evolving the AI models, AI pipelines. In Leiden, they are more focused to the evolutionary algorithms. So they are also working Llama and HPO, and they are also connected to hyperparameter optimization. Why? Because why to, let's say, spend the money, tokens, to ask GPT to give you the best parameter structure? It doesn't make sense. So it evolves the pure algorithm with some configuration space. So you will ask the LLM, hey, give me the algorithm and give me also some ranges and maybe pool of the parameters that should be somehow, let's say, optimized. And then you run secondary optimization, which is cheap. You can run it on any kind of the computer. And maybe, I don't know, this, you know, your colleague who was working here 2 weeks ago, Manuel Lopez Bañez, you know, maybe he developed the IRAs. I think that he co-developed the IRAs or something like that, which is basically hyperparameter optimization framework. So you can run these IRAs on any very cheap server, you know, to do it. So the LLM will only give you, hey, this is the algorithm, and this is the space, how you can yourself find the best parameters, because I recommend that you should look at this parameter, this parameter, this parameter, with this range, from 0 to 7 to 1.1, with this step. And you will do it. You will do it separately, and it worked, you know. And the guys in Leiden, they have tested for build-packing problem and TSP. They have a nice publications for that. In build-packing problem, these Llama HPO, this is the blue lines, was quite good. Also, the real Llama, some at the end beat it, but from the beginning, they were very good, you know, with the performance. In TSP, to find it was the same. You know, immediately find the best solution with the hyperparameter setup. So after a few iterations, it evolved it, and so on. And of course, they also created the Bayesian optimization version. I don't know if you studied Bayesian optimization. It's super complex. But they also created the HPO, which is again the same. They only synthesize the Bayesian optimization, the algorithms. The Bayesian optimization is more about the philosophy, the very complex philosophy, how to get the algorithms. So they have all this. If we conclude this, all these frameworks that we are using for automatic evolution of the algorithms and so on, there are a lot of lessons learned. These two frameworks, can very easily, can effectively find strong algorithms that compete and sometimes surpass state-of-the-art algorithms. I showed you in some examples that just think about that. You are engineering in Boeing. Oh, not the Boeing is not the one. They are falling, you know, Airbus. And someone will tell you, okay, hey, I need to have this better design of this and that. You have no idea about the AI. You have no idea about the evolutionary algorithms. You have no idea about the computer science. You just only, hey, I saw some framework with some, you know, front end. I can click somewhere, describe the problem, put some data, and it will give me the algorithm. It will give you the algorithm. Of course, you don't understand, but you should understand, you know. But at least you get something, you know. So and sometimes it can be the state of the art, which is designed. So sometimes we can get very strong algorithm just for the first run. The Llama BO is the first and only method that can generate the Bayesian optimization algorithms. What is really nice that all the generated algorithms we have tested can generalize to high dimensions or to even benchmarks, different problems. So for example, the algorithm which I generate for this time delay optimization problem from Continental, I have used the same algorithm for another problem and it worked also. So basically, some engineering problem algorithms can somehow generalize, like no method, no Fibonacci theorem. So it can really create the strong algorithms. But of course, you need to check it. You need to understand. You know, you need to somehow, you know, get inside and see what is really happening. This is why I said that this is very good assistant, but you should not rely on it. In case of interpretation, the Llama and ETSI, they are universal modular frameworks for algorithm constructions. You can construct whatever you want. Oops. And what is good? It works with continuous combinatorial Bayesian and other types of optimization. You only need to describe the problem and describe how to evaluate the problem, and then let it run. And of course, these lessons learned from these small case studies I show you are already inbuilt in the frameworks. So checking of these feedback, checking of something and so on. Of course, the LLMs or the generative AI can hallucinate, can create some stupid things. So then there's you as a human, as you will check the last working algorithm or the process of the iteration and see, okay, this one algorithm is super complex. It's somehow stupid, or maybe there's some mistake, I can see it. Or maybe this is not the right fit what I want to. Maybe I want to change it, refine it, so you run it again, or you rerun it. But still, there must be some human in the loop to check it. But it's a very good way to maybe improve something and so on. It doesn't mean that you should stop studying, because you need to really understand, you know, what is happening. But these things, they really work. And I show you there are evolution principles for LLMs for evolution principles, and all the words are interconnected. Since we are already talking for 1 hour and 30 minutes, I will skip the remaining 20 slides, because I just wanted to show you in details the, let's say, how to ease this. Okay, this is a marketing for my framework. Let's skip the marketing. But since it is recorded, so I can just simply click, very quickly click. So basically, we were describing the modules, all these prompts, how it works, how you specify the roles, and so on. Then how you connect the models. As I said, you can run whatever you want, or not even the LLM. It works with any kind of the random generator. You can randomly generate something, you know. So so we have the connectors. In case of analysis and test modules, you can run syntax checks, unit tests, keywords presence, and so on. You can use any automated feedback tests. So, but you need to craft it, because you need to understand the problem. You need to craft it, what to check, how to check it, how to evaluate it. So even though, and this is very important message, even though it seems like the LLM or these Google, ETSI, Llama can do anything automatically, that's not true. Because someone needs to describe the problem properly, so the Gen AI will understand. Someone needs to design the test modules. You need to know what to test and how to test. someone needs to decide the evaluation modules, how to evaluate the problem, how to, tell to the LLM what is wrong and what is good. So you really need to design and understand. And then you have these evaluations. So you need to define the quality, I don't know, fitness scores, heuristic rules. You can look at the maybe multi-objective evaluation, whatever. Or you can, all the additional metadata, you can analyze the code metrics, sentiment, images, lot of the things. It depends on the problem. You need to understand the domain, of course, to know what to analyze and how, and what to evaluate and how. And at the end, you need to define the stopping criteria, of course. What is the maximum iterations, maximum tokens, fitness? This is very, very tricky. Fortunately, we had only $100 loaded into GPT API. We just forget to put the stopping criteria. And after half a day, why is it not doing anything? It was like, oh, we don't have money already. So it was running infinitely. So there are a lot of customizable modules. And I just want to show you one thing. For typical tasks, algorithmic design, you can also generate the text. You can generate the image. Do you know the game 2048? Yes, someone yes. We simply prompt the ease to give us the solver, some optimizer, how to solve the game. And it's quite complex. I don't know if it will run. It's not running. I don't know why. Oh, the wheels are turning. The computer is quite overloaded with this because there are like a lot of videos running on the background, but it cannot see it, unfortunately. But what we'll see here that in first iteration, basically there was no solution. Second iteration, a couple of solutions, a lot of solutions, even faster, even better, and so on. So the ease was prompted to optimize the solver for 2048 in iterative way, and it was working. Okay, so now I just totally freeze my computer because these couple of videos is not good. Which is sad because I wanted to show you this QR code with some nice video how to generate the image. Okay, why is these things happening?
Presentation.
Yeah, we need to kill the presentation and so on. So. Okay, yeah, Microsoft PowerPoint is not responding. That's very surprising. Okay. So I will just get it back with the QR code so you can see some nice videos. I will skip the video one. And we are getting here. Okay, yeah, it's still presenting. Yes, good. So if you are online or then later after recording, you can just scan this and there's a video how to use the EASE framework, which is downloadable to automatically in iterative way generate a picture. Just instruct the, we have nice videos how to, let's say, improve and improve and improve. It's very simple. Of course, there is some token to GPT API. The token is fake, so don't be saying, oh yeah, free token. No. So there's a nice video. The EASE framework, if you just type my university AI lab EASE front end, back end, again, all the documentation is there. Also for the guys in Lamea, you can just, if you put Lamea Leiden University, you can find the documentation, GitHub, repository, Jupyter notebooks, and so on. So it's really, really easy to deploy. And that's it. This was generated by EASE. We instructed to improve and improve itself to make surrealistic Mona Lisa. And it looks, I think, good. So thanks for attention. And there's a huge credits to Nikki van Steen from the Leiden University for a lot of the slides and cooperative process. And also, if you want, you can just ping me an email or ask Carlos to just connect us and so on, and that's it. Okay, so thanks again. And questions, I suppose.
Yeah. Question time, so please feel free to.
I know it's.
Yeah, there's a question.
But maybe just first one, regarding cost, you mentioned cost. I have the feeling you're not querying the a lot, but then you mentioned, oh, you're using $100. That's a lot of queries. So can you explain why you were using so much time?
Yes. The problem is that if you do this iterative process, you want to, with the feedback, you want to keep the context. So it means that the LLM is always, in next iteration, you put there inside all the previous codes and results and feedbacks and so on. So basically, for example, for first iteration, you spend 1,000 tokens. The next iteration will be 2,000, then 4,000, then 8,000, and it's growing because you are just loading the full history there. So it means that then it can really get out of the control. So the cost can be sometimes high, sometimes not. But for example, to evolve the working algorithm for some particle engineering problem, it usually costs us like, I don't know, $2-3. If you compare it with the researcher which is working for 1 year to solve the problem, it's just nothing, you know. But then you need some one day to check it. So then you need to pay yourself and the colleagues. But it can really get very quickly out of the control. Yeah,
like LLMs are good working with domains that are very, let's say, popular because they have lots of information. They're not so good at working on domains that are, there's not a lot of information out there. So I was wondering if you can comment on that.
Yeah, because we have a super experience with that. Because of you students, we were thinking in, for example, you just think about the basics of, I don't know, C coding. If I give you some simple task, everybody can just prompt the GPT and get the tasks finished, you know, and just then you just, and this is pretty easy. We're thinking about the tasks that the GPT does not know. So we were searching the domains and so on, like, okay, so for example, some super crazy programming languages to prompt the 3D printer and so on. This really, let's say, rare domain. Of course, if the students they need to solve the task from the GPT, there was rubbish results, you know, because there was not enough, let's say, material to learn from. But this is what students doesn't do, is that if they get the response and prompt the GPT again, like, hey, can you improve it because? Then it gets better. You get something better and say, hey, can you improve it again because of this? Then it gets even better. So even though you started in some absolutely random domain, and you can get some reasonable feedback, but this reasonable feedback needs some domain expert because you need to construct these experts need to construct the feedback. Then you can get very easily some results. And that's why in documentation of both Llama and ETSI is written that you can use any GPT, any AI model, or any generator, which has no idea about, absolutely no idea. But these, let's say, constant and iterative improvements can create a complex and maybe working solution. It's not guaranteed, of course, but it can help a lot because we find it out, because we had experiences year before. We said, oh, we need to find some tasks so students will not cheat with the GPT. Now we are doing the opposite things. We are giving you, in our university, giving to students very complex tasks and simply say, hey, use the GPT, but describe the full process. All the prompts, all the challenges, all the problems you get, how you solve the problem, how you solve this, and so on, you know. But from the beginning, we were just thinking, hey, you know, they will be cheating. We need to find some really niche, you know, really small niche where we will just find out. But then we use it again and simply say that, find out that if we iteratively try to improve it and ask how and why, or why maybe to improve it, or maybe what was the bad on the previous, it gets better and better and better. So I don't know if this is a response for your question.
That sounds reasonable.
Yeah, it worked, but not every time. No, it's not guaranteed.
Someone you said that this could be automated, but then you also said, oh, a human has to look at it. So can you explain a little bit more? If it's semi-automated or completely automated?
It can be fully automatic, but then you just simply take the result and use it, and hope that it will be fine. Or you can observe it. Because everything is logged. So I mean that we keep the logs for all these steps of the process. In Lamea is in both frameworks, there are logs for each steps. You know, what was the population? I don't know, what was the solutions? What was the cost? What was the test? And so on. So basically, then you can come back, roll back, and analyze the results. Of course, maybe, or you can do this semi-process, so you can keep it run for maybe 5-10 iterations and then observe what is happening. If something bad is happening, like you are decreasing instead of increasing, you can restart the process with some different settings. Or you can let it run and hope for the best.
Because we have also observed in general that if you ask LLMs to fix something, they might fix it, but then afterwards they do some other error, and you sort of oscillate. And never get
or
exactly.
It's like basically it's a theoretic, some sort of reinforcement learning, just oscillating, and basically sometimes there's no stabilization. And this is a very good point, and this is what I showed, that sometimes you get some improvement and then no recovery. But this is something, again, you need to do it in few ways, in small batches, and reiterate the batches, and that they get one. I think that in these EOH or the re-evo frameworks, they have solved it with sort of elitism. So they always keep the best solution, like a best working code. So they are not refining it and so on. So in population, but we also keep it in log. So basically, you can roll back, you know, for example, in our framework, because you have the full window, you see the prompts, you see the results, you see everything. So you just scroll with the window. Okay, I will pick this one. Or you can just believe that it will work. So you can run it, you can take the result and deploy it and hope it will work, or you can check it during the process. So there are all possibilities. There are both possibilities.
More questions?
Chat.
Questions? Yeah, I do have a question. It's not so much technical as maybe philosophical, because well, you have mentioned the good and the bad of this approach to algorithm design. Focusing on one of the, let's say, bad things you mentioned, the ethical issues, like the scientific changes. So and find a connection with something that you really mentioned, not at the end, but was some kind of remark that you made, that you were mentioning that these AI models, like I don't know the sort of what you mentioned, like a powerful companion or a powerful collaborator. I think you mentioned something like that. And these somehow relate this. You know, when I was a child, we always had this image of the future in which machines. At the time I was a child, I'm old enough to think of the future with robots. So robots would make the work, and the humans would just do the creative thing. It turns out that it's the opposite. That really the machines are doing the creative things. Like actually this you have been talking about, essentially a creative thing. So my concern is, or my question, or my reflection on, I would like to hear what you think about that. What would happen if a few years in time we are able to solve some of the problems that you have mentioned about the models, the explanations, and all these things? And do you think that it can be danger or risk? Not just ethical, but the fact that we may lose knowledge because we do not really understand what is being made and we cannot recover that knowledge.
Okay, yes. And unfortunately, I think that this is already happening, that more and more we are relying for the, let's say, modern tech. We are losing this, I don't want to say like a sixth sense, for something. You just feel that this is the right step, this, because, okay, like 1 year ago, okay, I was thinking that this is the best thing, and it was not, but this time I really think that it will be the hit, so we maybe can lose this. I don't want to say something like a reflexes, some like a primary reflexes, but we can maybe a little bit lose it because we can rely more on technology about this. And the truth is that creative stuff is now done by the machines, but at the same time we have more time to focus on maybe exploration, how to use it, where to use it more, and maybe how to use these principles and so on. We were talking in the afternoon, for example, this framework we have been asked by the IBM company if they can implement some of the idea to some healthcare software for the breast cancer detection. Because for these AI machine learning models, there's one problem. You have different hospitals. Each hospital has a different, different equipment, different data available, different modalities. You have MRI images, you have these scans, you have these data, you have this. Another hospital has this. Another hospital has a small data size. So they simply say, we want to do that each patient will have evolved own AI model, for example, to detect something. So instead of static models that are super fine-tuned somewhere, but then it's deployed in 5 hospitals, and here is working good, here is not, here is working bad, here is perfect. So each patient, not just hospital, each patient will have own AI pipeline evolved for the particular, let's say, personality, for the particular data available and so on. So it means it can open up, let's say, a completely different chapters of how we do the things. So maybe we can do the things, we can engineer the things in different way, but the truth is that the algorithms and so on will be crafted by the machines. And I think there's a paper from 2024 from Tomas Bata from ETSI from Brussels, and he has written the paper something like, we should let the algorithm design and this crafting stuff, we should let it to machines. But we as humans can now observe why they have done that, maybe how to instruct them to improve it maybe even further, and so on and so on. So he has written a paper, let's say, no more handcrafted algorithms. We should move our, let's say, the exploration capabilities, the sixth sense, critical thinking. We should move it to how to, let's say, employ it in the best way, how to improve these, even, let's say, automatically generated model. So I don't think that it's danger. It depends on the deployment, but there's a risk that we will keep this, let's say, all this algorithmic thinking and this crafting of the algorithms. We will just, let's say, outsource it to the machines, and we will more focus only on these engineering ideas, how to make it better, where to deploy it in better work, and so on. So we can lose some basic instincts, let's say instincts this feeling like, okay, if I change this in the code, maybe it can work better. If I change this, it can work better. That's true. We can really lose it, you know. But it's hard to say now, you know. It's like,
and there's another angle, which is accountability.
yeah.
So who's responsible for the consequences of that software?
And that's the question of the lawyers, you know.
Yeah.
It's not still unsolved, no, because there's basically, to be accountable, you need to be a person. The machine, the robot, the AI model is not a personality. It's not a person. So you cannot make it accountable. It's not a management structure. You cannot make it accountable. And now what? Who is accountable? The last programmer which hit run, or the programmer of the framework, or the programmer of the AI model, or the programmer of the unit test function, which is used in some framework,
Or the one who provide the data for the training,
or the data, you know, or the data vendor, you know. Now it's super complex, you know. That's super complex work. So we will see what will happen, you know. But the true thing is that if we want to get some really quickly working, maybe proof of concept, the POC algorithm, we can instruct the system to behave and so on. But the most important thing, and that's why we had this lesson, is that you see that even though it was about the LLMs and some algorithm discovery and maybe some LLMs and this, still it was using the natural idea of survival of the fittest, of the improvements, of iterative process, of mutation and so on, some small changes and so on. So because this principle, this, I want to say evolution learning, it's evolution learning. This evolution learning is with us everywhere, even with these super modern frameworks. So that it's very important. For questions? Yeah.
I have two questions. Sorry for my English. I will try to make some. And in line of the question of I want to know. I have the feeling that these algorithms, that these frameworks could be the end of the originality in programming. Due to if I'm not sure about that, I'm asking for that. If those algorithms became in the state of the art of the algorithms, and all of the algorithms are well in this way, then these algorithms could be original. I don't know.
I understand. You know. So let's move. Let's say back to the future. Let's move like maybe in 5 years. We will meet in some big congress, and let's say all the algorithms that are in some competition or in research papers are artificially generated by LLM. And now, is it like original research work? And we have this discussion also, like maybe now, and again, this is like this from this Tomas Bata paper, that maybe the algorithm itself will not be the original work, but maybe the way how we generated this algorithm, how we check this algorithm, how we control the process of the evolution of the algorithm, maybe will be the original work.
Yeah, but this algorithm, this kind of progress, these models learn from the previous code. So if we don't generate new code, how these algorithms will progress? How can we push these results beyond these actual results?
This is very good question, and I'm getting the question every time when I'm because I'm also doing some lectures about the generative AI, basic of AI, and let's say using of Gen AI in companies, and they simply have the same question. And also, it's also philosophy questions. Just think about that. The first generation, because this is the same, the first generation of GPT-3, GPT 3.5 has been learned on maybe 95% of human-made content. The GPT-4, 4.05 has been already trained on some human-made content and a lot of the trash from the AI. That's true, yeah. And now what? then we have a next generation of AI models in a couple of years, and maybe the ratio will be very, very, let's say, small towards the human-made content and the AI-generated content. And now, this is very good, you know. What is then maybe the original idea? Is it something original, or it's just some reiterating already generated stuff or regenerating generated stuff and so on? It's hard to say, you know. In case of maybe some art or texts, it's difficult. In case of maybe the algorithm or the engineering, there is one important thing, that the AI itself, and thanks to this stochastism and all these, let's say, evolution algorithm and let's say the evolution learning principles, thanks to this stochastism, can sometimes discover something absolutely new, which is super, you know. I removed a couple of slides from this presentation when I was talking about very interesting LLM-driven framework, which is used for, I don't know, antibiotics discovery, drugs discovery, and so on, because the human-made engineering was not able to push it anywhere. But then the generative AI came and just create some absolutely stupid thing that we will not think about that this may work. Because the thing is that we as humans, we are usually biased. Like, I'm doing these experiments for last 10 years. So basically you are still stuck in the bubble. You are not looking outside of the bubble. The generative AI, thanks to combining even the rubbish, even the, let's say, human-made content, can sometimes leave these bubbles and can come up with something really breakthrough. But maybe it's not a full question to answer, that we can really generate something that it can help us. But the originality, or maybe the question of, is it worth it, or, you know, what will be in the future? I think I'm a bit sorry that I don't know how to answer for that, because there are like thousands of answers for thousands of people for that. That since you cannot link it to any previous generated stuff or human-made stuff, so basically you never know if it somehow originates and so on. Maybe, but it depends on the instructions. For example, in these frameworks, we usually try to tend to instruct that the models will start with some really handcrafted, manual, human work baseline. So we always say, okay, start with 99th version of differential evolution. Start with random search as baseline, as a source of your ideas. Then, of course, it can hook all this rubbish that has been generated past 5 years, you know. We don't know, but maybe thanks to this stochastism and maybe this, you know, looking out of the bubble, it can combine some crazy thing that has been crazily generated before, and it can kind of something very interesting, but depends on the luck, you know. But this is a very good question, and I'm getting this every time. You know? What will happen in 5 years? Maybe the AI will be more stupid because it will be trained on rubbish that has been generated by now, that, you know, all these AI videos and AI images and thousands of images of kittens with 6 paths and 2 tails and so on. You know, what will happen with the next models, you know, that has been trained on some crazy images and the crazy thing that the people are creating. But think about that. GPT 3.5 and 4 was mostly trained on the discussions from Reddit and so on. So it's not stupid, you know, at all, you know, like it still can do something, you know. But you are really right. You are on the good pathway. And that's why I said that the humans should still be there to simply instruct where to start, control the process, see into the logs, what was happening during evolution, and simply check, I can get these fantastic results, but through these steps maybe. Okay, let's count it as a good thing or not, I don't know. Or you can just keep it as you just close your eyes and let it run and say, okay, give me something, and you are happy. You know, and there's a big problem, and the difference between maybe you as a student, as maybe researchers, that you want to know maybe why, what is happening. And there's a big difference between the industry, which I was talking in the beginning about this black box optimization. They don't care how. They just want any kind of solution, which will give you in next day. It will cost them $5 for tokens, and they are super happy, and they don't care about anything. So there's like industry, research, understanding, maybe some human desire to know why, and there's a clash between all these fields. Because I'm getting there everywhere, because in industry, this continental company, they simply say, okay, just give me anything, it will work. Or with ease, we have solved the problem that the one company, some IPTV provider, that if you have an IPTV, you can just rerun any, I don't know, TV show, couple of days. But of course, the EPG program and the real start is somewhere different. There's a difference. So basically, if you want to run it again, you just always start somewhere else. Then you need to scroll a little bit further and so on. They ask us, hey, can you give us some machine learning model that they will detect the real beginning of this? But then there's a problem because you have an advertisement for next, we have this and this and everything. They have spent 3 years with all these graph attention, neural networks, whatever, testing the models and so on. And we instruct in the ease, hey, this is the data set. Can you find the machine learning model that can classify the beginning, the end, this frame? We found it in half day. And it was just some XGBoost, some small machine learning, some small neural networks, some ensemble system with 3 simple classifiers, perfectly weighted and perfectly fine-tuned. And it worked. They don't care how. We just gave them the solution. They gave us 100 euros. They're happy. But, you have very good ideas. A good question.
The questions? Any questions from the people online? So, okay, so let's thanks again Professor Schenkering for the great. For having me here.
Yeah, thanks for coming. I hope that you like it.
Interesting. Yes. How did you classify how to evaluate jokes? You were talking